In this video, I want to introduce the integral test. This section will have to be broken down into a few videos, but in the first one, I just want to introduce the idea and explain it. And then in future videos, what we'll do is we'll do some examples and we'll see how it works in action. But the integral test is going to be a test where really what we're going to do at this point in chapter 11 is I'm going to give you a series, and then we just have to decide, does it converge, does it not converge? That's the only thing that we're worried about. I don't want to say we don't care anymore what it converges to, but that's not the main point of doing what we're doing now. We just want to know, if I give you a series, does it converge or does it diverge? Actually evaluating the series can be really, really tricky for series. It's even harder than evaluating lots of integrals. And so all of our attention is just going to be paid to the much easier question of, does it converge, does it diverge? And so the integral test is going to be the first or maybe the second test that we have. I guess we can think of the divergence test as being kind of the first test. We know that if the sequence that we have, a sub n, does not converge to 0, okay, so if we have a sequence a sub n and that does not converge to 0, then the series diverges. Okay, so we know that if the values don't go to 0, the series diverges. We can kind of think of that as the first convergence test or divergence test, however you want to think about it. The next test, and kind of the first one that is beyond that basic divergence test, is what's called the integral test. And what I want to do before I actually describe the integral test and write it down is I want to do an example. I want to show you how this works. And I want to consider the series 1 over n squared. 1 over n squared is actually a really famous sum, and we'll talk about this as we go through. It turns out, well, I don't want to ruin the story, but if we write out the first few terms, it's going to be 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared, 1 over 4 squared, and so on, 1 over 5 squared. Okay, and so that's the integral, that's the series 1 over n squared. Now, what I want to do is I want to compare this to the integral of 1 over x squared, as x goes from 1 to infinity. And so if we want to think about this integral of 1 over x squared, what we can do is we can think of, I'm basically going to draw a big picture here, and I want to have both the integral and the sum appear in the picture. Okay, so I'm going to need some help here to draw a straight line there. There we go. And let's look at the values at 1, 2, 3, 4, and so on. Okay, and so we know, I'm going to make this as accurate as I can. So we have 1, we have, let's call that about 1/4. So here I'm just kind of eyeballing this, but we know that at 1, the function's going to be 1, and at 2, the function's going to be a 4th, and at 3, the function's going to be 1/9. And so the curve that you get when you're looking at f of x is 1 over x squared is going to look like this. Oops, I still have that tool on there. So you're going to end up with some sort of a curve. It's going to look like this. Let's pretend that I meant to put that point on there. Okay, and so that's what the curve is going to look like. And then we're looking at the area under the curve from 1 to infinity. Okay, so of course we know that that's this green area here. This is an improper integral. We could actually evaluate this integral. This might have been one of the first integrals that we ever evaluated. This is the limit as n goes to infinity of the integral from 1 to n, 1 over x squared dx. And 1 over x squared integrates right away. We don't need to do any substitution, nothing fancy. This integrates to negative 1 over x. And so when x is n, well, what it turns out is when you plug everything in, you're going to end up with 1 minus 1 over n, and this limit's going to end up being 1 as n goes to infinity. So it turns out that this converges. This sum converges. Now, what I want to do is I want to compare that to the series. And I'm going to make the series, here I'm going to think about 1 plus 1/4 plus 1/9. And what I want to do with that is I want to draw over top of this image that we already have a rectangle of area 1. So we have area 1. Okay, so the height of that rectangle is going to be the value at the left end point of the rectangle. And then the next rectangle will be 1/4. And then the next rectangle is going to be 1/9. I can't even draw straight lines with the help of my iPad here. So 1/9, whatever. And then 1/16, and so on. Okay, and so this red area is going to turn out to be what we're looking for when we find the series. So the green area, the area under the curve, is the area there. And in fact, maybe what I'll do is I'll shade the area that sticks above the function but below the rectangle. So I'll color that a red area. Okay, and so if I add up the red and green areas, that's going to be the value of this series. And so what's obvious, and what should be obvious, is that the integral and the series have two different values. The area of the integral is the area of the green part, and the area of the series, the value of the series, is going to be the area of the green plus the red part. And so the series is going to be larger than the integral. But what turns out to happen, and this is a cool little trick, is what you can kind of do is you can take this piece that sticks above the curve and you can slide it over so that it's between 0 and 1. So you can think of this piece, and I'm going to draw this in orange here. You can think of this piece as kind of being slid over, and it's going to be something like that. That's the amount that sticks up above the first one. And you could do it again with the second piece, slide it over. That's the amount that sticks up above the second rectangle, and above the third rectangle, and above the fourth rectangle. And in particular, even though they're not the same value, what ends up happening is that they differ by at most 1. And I know that if I add up these infinitely many orange terms, they can be at most 1 because this is a rectangle of width 1 and height 1. The rectangle itself that all these orange pieces are in is going to have area 1. And so what that means is that even though these have different values, what ends up happening is that the integral 1 over x squared and the series 1 over n squared, again, are not going to be the same value, but it turns out that 1 converges if and only if the other converges. So if and only if the series 1 over n squared converges. Okay, and so since we know that the integral converges, because we know how to evaluate integrals very nicely, that tells us that the series has to converge too. Not only that, but if we draw this picture, we realize that the series can be at most 2, because it's going to be the value of the integral, which we've already decided was going to be 1. We did that up here. And plus this little bit here, okay, which is, again, an area of at most 1. And so what we get from this is that the series 1 over n squared has to converge. And not only does it converge, but we know that actually the value is less than 2. Okay. What ends up happening, there's a mathematician named Euler. He's the namesake of the number E, 2.718. He was a relatively unknown mathematician until there was what's called the Basel problem. He was from Basel, Switzerland. Basel, whatever. B-A-S-E-L. And anyways, as a very young mathematician, I think he was 17 or something, he actually proved that this sum converges to pi squared over 16, which is like 1.6 something. Nobody had ever known exactly what that value was before. This is an incredibly tricky sum to evaluate. We're not going to do anything like it in class together, but this is kind of why it gets his name. So this was kind of his first claim to fame. And again, this is the mathematician Euler, okay, who proved that. So anyways, this is exactly what we would expect. Pi squared over 6 is 1.6 something. That's less than 2. And it turns out that the integral converges if and only if the series converges. And so this is going to go both ways. So what I'm going to do is I'm going to stop the video now. In the next video, I'll describe the integral test as a whole. And then after that, we'll come back and we'll do lots of examples. And we'll see that we have extra reasons for the harmonic series diverging. We'll talk about the integral 1 over x to the p. So there's lots of nice stuff that we can tie together at this point.